A very good day to you all, students. We want to continue with the topics acid, base, and salt that we started last 3 weeks. My name is S.Adebayo. We treated acid, treated the strong, weak acid, properties of acid, reactions of acid. Thereafter, we talk about the uses of acid, talk about base, alkali, talk about the reactions, how do we prepare base, and the likes. But the aspect, which is the last aspect of this particular topic, is salts. And today we shall be talking about the characteristics and definition of salts. How do we prepare salts, and what are the types of salt that we have? And lastly, what about the uses of salt and hydrolysis of salts? Salts. A salt is formed when all or parts of ionizable hydrogen of an acid is replaced by metallic or ammonium ions. Don't forget, we said that an acid that completely ionized is a strong acid. We said the one that partially ionized, we say, is a weak acid. Whenever acid reacts with base, it's either we have the hydrogen ions completely ionized, that is if the acid is strong, or partially ionized, that is when the acid is weak. So when the parts or all of the ionizable hydrogen of an acid, because every acid have the amount of hydrogen that can completely ionize. That is what we talk about when we're talking about the basicity of an acid. That is the number of hydrogen that can ionize. The ions, the hydrogen ions that can ionize. Some can completely ionize, some will still ionize part of them and still retain, like the methanol, the C3COH that we talk about, which out of the 4 hydrogen we give out 1 to ionize. But the likes of HCl, H2SO4 acid, they will release all the hydrogen ions to ionize. So a salt is formed when all or part of the ionizable hydrogen of an acid is replaced by metallic or ammonium ions. Whenever the ionizable ions, the hydrogen part of an acid ionize, definitely there will be a kind of replacement by the metal that is displacing it. So as a salt consists of all aggregation of positive charged metallic ion and negative charged acid ions. We shall know more about this in our next slides. Characteristics of salts. The first one, or the first characteristic I want to talk about here, is water of crystallization. These can be defined as a definite amount of water that some substances chemically combine with when they form salts. And such salts are referred to as hydrated salts. Now, basically, we have hydrated salts and we have anhydrous salts. I said we have hydrated salts and anhydrous salts. Any salt that is hydrated means that it contains water. It is mixed with water. That's what the word hydrated. That's what the word hydrated means. And the anhydrous means it is dry, not containing water. So any salt that contains water of crystallization or that contains water is said to be an hydrated salt. So the water of crystallization is a definite amount, because there will be a kind of defined amount of water. It might be 10 moles of water, it might be 5 moles of water, a definite amount of water that some substances chemically combine with when they form salts. And such salts are referred to as hydrated salts. So hydrated salts are salts with water of crystallization. I come again. Hydrated salts are salts with water of crystallization, or simply hydrated salt are salt that has water or that contains water. So when we then eat the hydrated salt, whenever we have any hydrated salt, when we subject them to eating, what happens? They give off the water content in them. Just as if when you mix a salt, a normal common salt, with water, put it on the fire, cook it, so that there will be a kind of evaporation of the water of the boiling. There will be a kind of vaporization of the water. So whenever any hydrated salt is then heated, they give off their respective water of crystallization, and so they become anhydrous. So I told you the main difference between anhydrous and hydrated means that hydrated means it contains water, anhydrous means it does not contain water. So whenever hydrated salts are heated, we have anhydrous salts. So when hydrated, they are crystalline in shape. So hydrated salts are crystalline in shape, but when heated and the water of crystallization is released or given off, they lose the crystalline shape. That means whenever any salt is heated, it's changed from being hydrated to anhydrous, and it also changed from being crystalline to non-crystalline. So anhydrous salts are non-crystalline in shape, but hydrated salts are crystalline in shape. Example of salt with water of crystallization, that is, example of salt that has water in the name is sodium thiosulfate 4 decahydrate. Don't forget, deca means 10. So that is Na2SO3 dots 10H2. That is a sodium triisocarbonate 4 having 10 moles of water. That is the point 10H2 there is the water of crystallization possessed by such sodium. The next one is iron 2 tetrasulfate 6 heptahydrate. Everybody knows that hepta means 7. Hepta means 7. So that means iron 2 tetrasulfate 6 with 7 moles of water of crystallization. And the last one is sodium triisocarbonate 4 decahydrate. That is Na2CO3.10H2O, and so on and so forth. The next slide talks about efflorescence. Sorry, this is not supposed to be here. Let me cancel it. It's supposed to be. Sorry, this is wrong. This is supposed to be salts. Salts. Sorry. Salts. Okay. Now, the second thing I want to talk about here is efflorescence. Efflorescence. We talk about the fact that any salt that has water of crystallization is said to be hydrated, and the one without is anhydrous. And that's what we call water of crystallization. Now, efflorescence is loss of part or all of the water of crystallization from a crystalline salt when exposed to atmosphere to form a lower dihydrate or anhydrous salt. Now, whenever some salts are exposed to the atmosphere, they tend to lose parts or whole of their water of crystallization. So they become now less, or they become a less dehydrated form. For instance, let's say we have a salt having 10 moles of water of crystallization. When the salt is exposed, it's either the salt will remove or the salt gives out all the 10 moles, or maybe gives out about 5 or 6 moles. So we still an hydrated one, but at least the water of crystallization have been given off. So when some salts are exposed, they tend to give out. That means they tend to be from a crystalline salt, because any salt that is crystalline is hydrated one, the one that has water of crystallization. They tend to give, or they tend to be from crystalline to anhydrous, or from crystalline to non-crystalline, from hydrated to anhydrous. So example of a salt that undergoes efflorescence is sodium triisocarbonate 4 decahydrate. That is the what we call washing soda. The washing soda is an example of a salt that has the tendency of giving off the water of crystallization to the atmosphere when exposed. Any salt that gives us water of crystallization, any salt that gives us part or all of its own water of crystallization to the atmosphere when exposed is said to be to undergo efflorescence. Such salt is an efflorescent salt. So there's efflorescent, that is the name of that salt, the noun. Why you have the efflorescence. The third point here is deliquescence. Deliquescence is a phenomenon in which a substance absorbs water or moisture from the atmosphere when exposed and turned into solution. Efflorescence is about when we expose a substance, it gives off water. The liquid is talking about whenever a substance is exposed to the atmosphere, it's now absorbed. It does the reverse of the efflorescence. It absorbs the water and turns to solution. Don't forget, if any something is dry before, absorb water, it turns to a solution. So it becomes more of water, of crystallization. It becomes more musty or more sticky. So any substance or the liquescence is a phenomenon in which a substance or a salt absorb moisture or water from the atmosphere when exposed and turns into solution. Example of the liquescent salts are calcium chloride, iron 3 chloride, copper 2 chloride, we have zinc chloride. So these are examples of the liquescent. So they are calcium chloride, iron, copper. They are said to be deliquescent. They are said to be deliquescent because they undergo deliquescence. I think you understand the difference between the two. Deliquescent salts are the salts that undergo deliquescence. So hygroscopic is another one, which is a phenomenon in which a substance absorbs moisture from the atmosphere when exposed and does not turn into solution, but may become sticky or moist. That's very good. You can see this now. There's a slight difference between deliquescence and hygroscopic substances. A deliquescent substance will absorb moisture and turn to a solution, but hygroscopic substance will avoid moisture and will not turn to solution. So both absorb moisture. That's one common thing between the two of them. The liquescent substances or hygroscopic substances are the substances that absorb moisture when they are exposed to the atmosphere. But the liquescent substance will turn to solution when it absorbs its own moisture, while hygroscopic substances will not turn into solution. They rather become more sticky or more moist. An example of hygroscopic substance is sodium thiocarbonate 4, potassium thiocarbonate 5. Hygroscopic substances are commonly employed as drying agents or desiccants. That's one thing I want to understand. Most of the like tetrasulfuric acid, that is the conk one, we use it to dry. Calcium oxide, these are examples of hygroscopic substances because they are used to dry. So most of these hygroscopic substances are used to dry, are used as drying agents to dry some gases when they are being prepared in the laboratory because they absorb moisture and do not turn into solution. So most of them are used as drying agents or desiccants. That's another name for dry agent, desiccants. Now let's quickly talk about that dry agent or desiccants. Dry agent or desiccants are substances that have strong tendency to absorb moisture or water. Yes, that's the reason why they don't turn to solution. They have a very strong tendency to absorb moisture or water. They are used to dry gases in the laboratory. And a drying agent cannot be used if it reacts with the substances to be dried. That is why H2SO4 cannot be used to dry ammonia gas, because they will react to form ammonium 6. Now, let me tell you, apart from that, the fact that drying agents or desiccants are substances that absorb moisture and do not turn into solution, and they are being used as drying agents, and they are hygroscopic substances because they are definitely hygroscopic in nature. Whenever I want to use any particular substance to dry any other substance in a laboratory, I must verify that there will not be a kind of reaction because we don't want our drying agent to take part in the reaction. So I should be very careful that thing that is hygroscopic in nature do not have any form of reaction with that thing I'm drying. Most gases are dried by use of H2SO4. But one exception is ammonia. Ammonia and H2SO4 is not used to dry ammonia. We use calcium oxide to dry ammonia. Don't forget, we need to dry some gases because most of the gases that we prepare in laboratory are still moist in nature. They are moist in nature. They have water. So when we prepare them, so that's why we need to now pass them through a drying agent or desiccant so that water aspect of it can be removed. But one common drying agent in the laboratory is H2SO4, which is the conk H2SO4. But it is not used to dry ammonia gas. Why? Because H2SO4 reacts with ammonia gas. That's the question you are looking at there. And whenever any hygroscopic or desiccant or drying agent react with a particular gas or any particular substance you are drying, we do not use it because it will take part in the reaction and it will not dry. It will rather react. So that is the reason why H2SO4 is not used in drying ammonia. So we rather use quicklime, which is calcium oxide. This is a past question. That's why I laid more emphasis on this aspect on it. A drying agent should not react with that substance you are drying. And that is the reason why H2SO4 is not used to dry ammonia. That is why we use calcium oxide, because calcium oxide do not react with ammonia gas. So desiccants are drying agents and they are hygroscopic substance just because they absorb moisture and never turn into a solution. Next slide is how do we prepare salts. The method chosen to prepare salt depends largely on the solubility in water and stability to it. That's the method. There are two methods here that we use to prepare. That is how soluble is that salt is in water and how stable will that salt withstand it. The first one, which is the preparation of soluble salts. Why do we prepare? Because there are some salts that are soluble, there are some that are insoluble. That is when they dissolve, they form crystalline form, they do not completely dissolve. Any salt that will not, like when you put gari inside water now, you can see what you have is insoluble because not all the gari dissolves. But when you put pinch of salt in water, what happens? All the salt disappear. That's exactly what we call soluble. So preparation of soluble salts. One, reaction of acid and metal. When you have acid with a metal, there is tendency that there will be a soluble salt formed. And a typical example is zinc reacting with hydrochloric acid. And you can see zinc chloride and hydrogen gas is being formed. So the zinc chloride there is a soluble salt. So whenever we react a very more reactive metal with an acid, there's higher tendency that a salt is formed, but hydrogen gas will be given up. And I must tell you emphatically here that this is exactly one of the main reactions or laboratory preparation of hydrogen in the gas, in the laboratory rather. Whenever we want to prepare hydrogen in the laboratory, we just have a more reactive metal with an acid. And that more reactive metal with an acid, we displace the metallic ion there, and hydrogen gas will be formed. The second one is the reaction of alkaline. When you have react alkaline with acid, don't forget an alkaline is a base, a soluble base. When we react an alkali with an acid, what salt will be formed. And don't forget, that is more or less a neutralization I talked about, because whenever you react acid with base or acid with alkali, you have salt and water being formed. And that is exactly what we call neutralization reaction. Reaction between acid and base to form salt and water. So the reaction we have in number 2 here is an example of that. The 3 is when we have dilute acid and insoluble base. When we have acid with a base that is not soluble, you also find salt. An example is what you are seeing on the screen, which is 2HCl plus copper oxide. You have copper chloride with water. Copper chloride is a salt formed there, and copper oxide is an insoluble base. Don't forget, any insoluble base will not contain H. When you have any base that have OH, most of them are soluble. The OH is from the water OH hydroxy group. Preparation of insoluble salt. The first set we discussed is preparation of soluble salt. Now, there are two. Are there two? Okay, let's just start. One, double decomposition. When we want to prepare salts, insoluble salt, we have double decomposition. And this is done by mixing two compounds, the one containing metallic radical and the other one acidic radical. An example of that is what we are seeing there. There is an acid and a copper oxide, that is a metallic radical and an acidic radical. That's what we call double decomposition. And the second one is combination of constituent elements. When we combine some elements together, we have insoluble salt. Look at the example of iron with sulfur. They are direct elements. When you match them together, you have iron sulfide. And iron plus chlorine 2, you have iron 3 chloride. That is another example. Let's also continue. We have types of salts being our next thing to discuss. There are 5 main type of salts that we have. We have normal salt, acid salt, basic salt, double salt, and complex salts. These are the 5 main salts. A student must be able to define and explain each of these salts. A normal salt, what is a normal salt? A normal salt is from when all the replaceable hydrogen ions in acid have been completely replaced by metallic ions. Don't forget, a replaceable hydrogen ions, if all of them, like HCl now, when you write HCl with a base or an alkali, if all the H is removed, like look at the first equation, second equation, HCl plus Na, you can see that all H has been removed and replaced by Na in the right equation. If all the replaceable hydrogen ions or the basic, when the basis of an acid is full, all the replaceable hydrogen ions of an acid have been completely replaced by metallic ion, then what we have is a normal salt. Excuse me. And the example of this is what you are seeing here, H2SO4 plus zinc oxide. All the H2 has been removed and matched with water, turned to water, and zinc replaced H2. Look at it, we have ZnSO4 in the right equation. That means all the H2 has been completely removed, replaced by zinc. There are 2 ionizable or replaceable hydrogen ions in H2SO4. There are 2. But all the 2 has been replaced by zinc in the right, you can see, and it's now there is interchange the zinc and the hydrogen has interchanged their position. Zinc goes to meet SO4 and H2 goes to meet oxygen. That is exactly what we call complete replaceable hydrogen ions that has been removed. Now look at this here too. HCl, in the HCl, we have H plus and Cl minus. In the NHOH, we have Na plus and OH minus. You can see all the cations, H and Na, has been interchanged. So the hydrogen ion, there is only one hydrogen ion in hydrogen chloride here, and it has been replaced by sodium in the right equation. So when everything has been replaced, that's the normal salt. But acid salts are formed when the replaceable hydrogen ions in acid are only partially replaced by metal. You can see an acid to litmus paper, and as acidic to litmus paper. Yes, when we say something is acidic, it must definitely be acidic to litmus paper because it will turn blue litmus paper to red. That's what we mean by being acidic to litmus paper. It will turn blue litmus paper to red. So H2SO4 plus sodium hydroxide, that is, you can see that it is 2 hydrogen ions that are replaceable in H2SO4, but you can see that only one has been removed. That is NaHSO4. Look at the SO4 in the right. H is still there. One is only one that has been removed. Whenever any acid, any salt is having H content in it, that salt is an acidic salt. You can see the H is still in. If it's ordinary NaSO4 now, that is a normal salt. But it is NaHSO4. The H means it is still contains some acidic content. Basic salt form when there is an insufficient acid to neutralize a base. Yes, because complete acid neutralizing a base is what we call normal salt. But when there is an insufficient acid to neutralize a base, what we have is a basic salt. For example, is calcium oxide plus HCl, and that one we have calcium. Now, what make a salt to be basic is the presence of the OH, the hydroxy group in it. That is just the clue. When you have a salt that have OH in it, it is a basic salt. And when we have a salt that have H in it, it is an acidic salt. Double salts are salts that are ionized to produce 3 different types of ions in solution. Whenever you can see that there are 3 ions present in a salt, usually 2 of these are positive while the other is negative. Potash alum, like normal alum that we use, is a double salt. Aluminum, potassium tetraphosphate 6, duodecahydrate, that's the example of a potash alum. The alum that we use at home, that is aluminium, aluminium, potassium, tetraoxide 6, dodecahydrate. That is dodecahydrate means 12. That is the potassium. When you try to ionize this or put this one, it will ionize it into their corresponding ions. We have the potassium, we have aluminium, and we have what we call the tetraoxide 6 ion. There are three ions. Whenever you dissolve, ionize any salt, and there are three ions, and most common when we have two of them to be positive and one to be negative, such a salt is a double. A complex salt is a salt that in water it causes form a complex ions. An example of that is the one that is the potassium hexacyanopherate 2 and sodium tetrahydroxozincate 3. That is Na2CN. These are complex compounds and they are complex salts. Uses of salts. What are the uses? First one, sodium chloride is used in preventing food. We know that. Sodium chloride is used in preventing food, preservating, that is preventing food from spoiling, rather. That is as preserving food. Salt are used as drying agent and antifreeze. Whenever we want to dry or we want to make sure that something does not freeze easily, we use salt to do that. Salt are used in making soap and also to separate soap from glycerin. It is also used in softening water. When you have, sometimes they say put salt, but in most cases when the water is too hard and you want to make it soften, we use salt. Most cases when you try to at least try to remove your dirt from your well, and they say put salt before it starts springing up, put salt and alum. It is only used to soften and to make a water to have a very good taste. Used in stabilizing dirty roots. And this last one is used in production of toothpaste. Most of the toothpaste you see, you can see they taste salty in our mouth. It is the presence of salt in the toothpaste. Hydrolysis of salt. When salt is dissolved in water, a solution which is either acidic or basic is formed. The reaction of salt with water to form acidic or basic solution is called hydrolysis of salt. When salt hydrolysis means when you dissolve a salt in water. It said that it depends on the type of salt you are dissolving. Any soluble salt or insoluble salt that will dissolve in water. If you dissolve that salt in water, it's either you have acid or basic solution form. Depending on if the salt is acidic salt, you have acid solution. If the salt is a basic salt, you have a basic solution. So when we dissolve salt in water, the process of doing that is called hydrolysis of salt. So hydrolysis of salt is dissolving salt in water to form either acidic or basic solution. However, when other salts are dissolved in water solution, they are not neutral, are formed. Okay, when we have some salt, that's what has been dissolved in water, most of them are non-neutral. The solution may either be acidic or alkaline. That's exactly what I described there. The solution of a salt, of strong acid and weak base will be acidic. When you have a strong acid reacting, salt are formed when acid reacts with base. So when there is a strong acid reacting with a weak base, or definitely the kind of salt that will be formed will be acidic salt. And when a weak acid reacts with a strong base, what you are going to be to get as a salt is an alkaline salt. So that is an examples of that is what I can see there. The questions that we see there is a typical example. Ammonium chloride is a salt dissolving in water. That is to find ammonium hydroxide plus HCl. That is a basic. We have copper sulfate, copper tetraoxide form. That's a basic. The first one, ammonium hydroxide, that's a basic salt dissolving in water to form a solution. That's a basic solution. Look at this now. The second one is also, we have the copper sulfate. We have the third one to be sodium carbonate. All are the salts. Potassium carbonate also dissolve in water to form either basic or alkaline solution. This is your evaluation questions that you need to provide answers to really ascertain the fact whether you have learned so far acid, base, and salt. I want you to just write this and do it in your assignment books. We shall reconsider when we shall check all this in few days. We shall call for it. So try and make sure that all your assignment from our week 1 is done perfectly inside your assignment book. I will be meeting you in our week 4 with another brand new topic. Thank you very much, and stay back. Don't forget that you have to subscribe and on your alarm in our YouTube channel so that you can keep on notified whenever any video is being dropped for you. Thank you very much, and have a blessed day.